Hello, this is Professor Dan Kernler, and this is our second video in section 16.4. We're going to do two more examples of volumes or triple integrals, easy for me to say, and then we're going to do one last example when we're integrating not just finding volume, not just integrating the constant one. So the first one here, we're going to do example 4, and this one we're going to just set up the triple integral, not actually going to find it. We've got the volume of the solid bounded above by the paraboloid and below by the plane. We're going to try to sketch what this looks like by hand, and then we're going to cheat using Maple. I have the graph up. We'll kind of double check. So let's draw our coordinate axes here. We have z, x, y. And then z equals 1 minus x squared minus y squared isn't that bad. If you look at traces, if y is 0, z is 1 minus x squared, and so that's a parabola open downward, crossing up here is 1. And same thing, if x is 0, then you have a parabola open downward. And so what we have here, oh, and then if x and y are 0, or sorry, if z is 0, you have x squared plus y squared equals 1. And so you have this paraboloid. And then what we have is we have the plane z equals 1 minus y. So let's take a look at what that would look like. If we have z as a function of y, 1 minus y would be this, but that's looking at it from the side. So that's kind of looking at it along the x-axis. So what that is that's a plane cutting through here and crossing at 1 and then cutting. That is not a good idea there. Let's do a different color. It's going to cut out a little bit of this here. And this is, I apologize for the analogy here, but one of my first jobs was at a little local like convenience store, and they had a deli. And I actually had the job there of slicing meat for people. And you have the little meat slicer. Do you know where this story is going? And at one time I like sliced off a bit of my thumb. And so I always think of that when I do this problem, is this, and it's good that I'm doing red here, this is like the bloody chunk of my thumb that got sliced off. It's so bad. But that's the volume we're going to try to find there. We're going to try to set up an integral that finds the volume of the chunk of my thumb that got sliced off. I actually played basketball the next day and had like a great game. I mean, for me, I scored like 8 points, which is my all-time high. Okay, getting distracted here. So let's find the volume. And so we will do triple integral over the region dv. Okay, so the z's are going to go, we've got our little representative z here. We're going to go from the bottom to the top. The bottom is the plane, and the top is the paraboloid. Okay, so z is going to go from the plane 1 minus y to the paraboloid 1 minus x squared minus y squared. And that's dz. And let's do y, and I don't know if we should do y and x next. Let's see. Because now I need to know, right, let me look at the maple here and pull that up. So there's my little slice of thumb, but now I need to know from above what that region is right there. And we've talked about this with some homework questions. That's the intersection of those two surfaces. So I think we need to find that next. So, oops, I went down too far. It's like no happy medium here. 1 minus x squared minus y squared equals 1 minus y. We've got the 1's on both sides. We can subtract 1. Let's multiply everything by -1. X squared plus y squared equals y. Solving for x or y here, neither one is going to be great. If we solve for x, we get y minus y squared. And so x is equal to plus or minus square root of y minus y squared. So that looks kind of gross, but what that is, we could do a bunch of algebra to show you. But that is actually a circle. It's actually a circle. It crosses at 0 and 1. It's a circle radius 1/2. That does not look like a circle. And I'm drawing like the left and right because what I have here is I have the positive x equals positive square root of y minus y squared. and then I have the negative, x equals negative square root of y minus y squared. Ooh, gosh. So because of that, because it seemed easier to solve for x, I think we should go horizontally next. So we did the z up here in the main picture, and so I think, oh, I lost my x-axis. What in the world happened to my x-axis? I think I accidentally erased it. I think what we should do next is we should add up in the x direction and get my little slice in the x direction. And so I think we should do x next, because I don't know how to solve for a y easily here. We'd have to use like quadratic formula. It would be even worse than what this is. So I think it's going to be easier to solve for x and say x goes from negative square root of y minus y squared to positive square root of y minus y squared. Now, if you notice here, there is some symmetry. If we look at the actual one, a little bit easier to see here in Maple, there is some symmetry with the negative and positive x values. So you could double from 0 to square root of y minus y squared. That would not be a bad idea at all. So then once I have the x's, then y goes, when I add up those slices, the top one here is at y equals 0, and then I add them up as we go down to 1. Y goes from 0 to 1. So that's the volume there of that slice of my thumb. Okay, let's go to one that's a little less gory here. We have this integral. Now we're going to do something a little bit different. We have the integral. We're going to try to figure out what it is that we're integrating over, and then switch the order of integration. Okay, so z starts at 0 and goes to square root of 4 minus y squared. That's a cylinder because there's no x. X is free, so we can move along the x-axis. X, y, z. Square root of 4 minus y squared would be a circle radius 2. And then we're moving along the x-axis. Let's see, y goes from negative 2 to 2. Okay, so it's the full semicircle. And then x goes from 0 to 1. I'm going to do out here at 1. So I'm going to basically draw another one out here at 1. And so that's what we have, kind of like a speed bump, or I don't know, right? I think I did a pretty good job drawing that one. Let's see. Yeah, right. Looks pretty good. That's what we have. Nice. Okay, so we are told to redo this integral. By the way, I've learned to kind of space out this one right here, because the x, or the first one here is the last one you do, and you're just integrating whole number, or just bounds, just real number bounds. The first one is going to be the most complex, usually it's from one function to another. The middle one, though, usually does have a couple terms, so it's good to leave some space there. So we want to go dy first, then dz, then dx. Okay, if we're going to go y first, then we have to start, like with our representative piece, it has to go from the left to the right. Right, we're going to get a little piece like this moving left to right. So let's look at that here. Boy, we have our z equals square root of 4 minus y squared. That's the curve. If we look at that in the yz plane, yz, just looking at it from the side, 2 and 2. If we square both sides, we get z squared equals 4 minus y squared, or y squared plus z squared equals 4. That's the circle radius 2. Now that's the full circle. We're just looking at the top half. But now I need the left side and the right side. That's this left side, and this is the right side. It's kind of like the bottom and top, like left and right. So I need to solve for y. And I say, well, y is this plus or minus the square root of 4 minus z squared. So y goes from negative square root of 4 minus z squared. That's the left part here. That's this left side over here. And then it goes to the positive square root of 4 minus z squared. Okay, and then once I get that, we're going to add these up vertically to get a slice. So that looks terrible, but we're going to get a little slice there. Z is going to go from, I guess, just 0 to 2. Usually it's more interesting, but the Z is just going to go from 0 to 2. And then we'll add up those slices to get the full loaf of bread as we go. X will go from 0 to 1. So there we have done, we've drawn the integration region, and then we've rewritten it in a different integration order. These take a lot of practice, by the way. This seems easy as I'm doing it. I should rephrase that. It seems like it's easy for me because I'm just kind of doing it quickly. Number one, I have a master's degree, so I have a little more practice than you. Number two, I have notes in front of me if I get stuck. So be patient, try a bunch of these, really practice. One thing you can do on your own, if you have an integral and you've done the integral, you could do that triple integral in Wolfram Alpha. Try to rewrite it and then type that rewritten one. Don't actually do it, but just type that rewritten one into Wolfram Alpha and see if it gives the same volume, same answer, because it should give you the same answer no matter how you reorder it. That's a good way to practice for yourself. Okay, last part here. So suppose we have a function that is a function of 3 variables. We have talked about this like mass or temperature. I've talked about that before. That's the example we're going to do. The average value, we denote that with a little bar over it, is, if you recall, do I have the average value from 16.1? Was it 16.1? There we go. In double integral for functions of 2 variables, it was 1 over the area, or the function of one variable is 1 over the length of the interval times the single integral. In 2 variables, 1 over the area of the region times a double integral. And so now we are doing triple integrals. Sorry, it didn't made me reset. That was annoying. And now we're doing triple integrals, and so now we would take 1 over the volume of the region, so in this case that's the region D is what we're calling, times the triple integral over the region D of the function f of x, y, and z, and then dv. And dv would be dz, dy, dx, whatever order you want there. Okay, so we are going to do one last example, and in this example we have a 1 centimeter metal cube that's 1 by 1 by 1, and we're going to center it at the origin to make things simple. Oh, that was a weird x, y, z. And we have a 1 centimeter cube. There's our 1 centimeter cube. And the temperature on that cube is given by this function, xy plus 8z plus 20, and that's in degrees Celsius. So I guess the largest temperature would be out at this far corner because x and y and z are their maximum there, they're 1. So the largest temperature would be, what would that be, 29. And then the minimum temperature would be at the origin is 20, and then the temperature varies as you travel throughout this cube. So it might have like a heat source at that top corner that's spreading the heat throughout the rest, and the cold, or maybe the corner is in, well, it's not going to be ice because that would be down at closer to 0 down there in the corner, right? So maybe there's a heat source up at this top right corner or top far corner here. We're going to try to find the average value. So the average temperature, T bar, would be 1 over the volume of D times the triple integral over D of the T function, dV. Now, conveniently here, the region is simply a 1 centimeter cubed region, so that's 1 over 1 centimeter cubed. And triple integral is about as easy as it gets here because z simply goes from 0 to 1, y also goes from 0 to 1, and x also goes from 0 to 1. So when you're finding the integral of a function over a cube, excellent. Any kind of rectangular prism would be nice. You just have constant bounds on all of x, y, and z. Okay, so I'm going to leave this 1 over 1 centimeter cubed because the units will make sense here. This is a degrees Celsius. I don't know if the units will make sense or not. So the temperature here is degrees Celsius, but then dz, dy, dx, they're all centimeters. So what you would get, I'm just going to leave this 1 over 1. What you would get is you'd get degrees Celsius times centimeters cubed for the integral. And then when you divide by centimeters cubed, you're back to degrees Celsius, and that's the average temperature. Okay, so let's integrate z first. So we'll have x, y, and then z, right? Because x, y is a constant with respect to z. And then 4z squared plus 20z from 0 to 1, and then we still have to do dy dx. And then we plug in 1, so we'll have xy plus 4 plus 20, and then minus, when we plug in 0 for z, everything's 0. And we're integrating that dy dx. And now we're integrating it with respect to y, so this will be xy squared over 2 plus 24y, also from 0 to 1, and that's dx. And then, let's see here, we would get plugging in 1 for y, we would get x times, let's see, x over 2. And then plugging in 1 for y there, plus 24, and then subtracting, plugging in 0 for y, we get 0, and that's dx. And then integrating with respect to x, we'd have x squared over 4 plus 24x from 0 to 1. And so finally, 1/4 plus 24. That's 24¼ degrees Celsius on average. Whew, so that is it for section 16.4. Let me know in the comments or via email if you have any questions, and I will see you next time.